Welcome back to Robotgeek 101. Today we're going to take a look at continuous turn servos. This is an extension of our Robotgeek servo video, so we definitely recommend that you take a look at that video so that you can understand servo pulses and the basic code for controlling servos. So before, with our joint servos, we were expecting to be able to send a signal 0 to 180 degrees and move that servo to individual positions. But we can never go past that 180 degrees, so I get stopped physically here. Now this 4C servo here looks identical to the 13C servo. It's got the same connector, same horns fit on it, same brackets fit on it. But the behavior is very different. Instead of having a physical stop, the servo can turn. So this is much what you might expect out of a normal DC motor that just keeps on spinning with no physical stops, no positional control. Great example of using continuous turn servos is our GeekBot rover. So just like a standard RC rover, you've got your two wheels on the bottom. Each wheel is connected to an RGS 4C continuous turn servo. So why use continuous turn servos instead of just a DC motor? Well, like we said in the first video, you need a control board to connect your motor to your Geekduino. This servo has all that circuitry built in. It's also really easy to mount using our mounting system and all of the plates that we've designed for the Robotgeek system. Now, for this servo, you are not able to control the position, but you are able to control the speed. So let's go ahead and put this servo in instead of our RG113. If you're unsure which servo you have, the label should tell you. 4C is the continuous turn, and the 13 is the 180 degree joint servo. You can also do what I just showed you, where you rotate the servo spline. The continuous turn just keeps going, where the 180 will physically stop. Now I'm just going to go ahead and put this on here. Because these are not used as positional servos, you don't have to do any sort of horn alignment. And as you can expect, when I start sending the signals, it's just going to keep going and going and going. So first, let's take a look at File, Sketchbook, Robotgeek Sketches, RG101, Servo, Continuous Rotation. All the functions that we use are going to be very similar to what we've used for our positional servos. We have to include our servo.h file, and our servo pin is 3. Our servo pulses are a little bit different. We've got a min pulse at 1200, our max pulse at 1800, and a stop pulse of 1500. So, like I said, instead of controlling position, these values are going to control speed on a continuous turn servo. Our stop pulse is 1500, and that just means servo, wherever it is, will stop right there. Our max pulse is full speed in one direction. Our min pulse is full speed in the opposite direction. And then any values in between are speed differentials on that rotation. So 1300 is a little bit slower, 1400 is a little bit slower, all the way to 1500 it stops. Then you start 1600, it's faster in the other direction, 1800 fastest in that direction. So we've got our servo1.attach. We're going to attach our servo stop pulse. And now we're going to use some loops. There are lots of different kinds of loops, but we're going to use a for loop. A loop is very similar to that void loop function in Arduino, that it just keeps running. Only these will have conditions. These conditions are based on the counter variable, so that's this first parameter. So we're going to start with int I, our counter, set to servo stop pulse, or 1500. The next part of the loop is I is less than or equal to servo max pulse, and this is the loop check. So the loop will keep running as long as this check is true. So when we first start, I is 1500, and 1500 will be less than that max pulse of 1800, so this loop can keep running. I++ is the incrementer. So this is how I changes. Every time the loop runs at the end, I will increase by 1. That's what this plus plus means. So I starts at 1500. After the first loop, it'll be 1501, 1502, 1503 as the loop increments and increments all the way until 1800. And once it gets to 1800, I will be equal to 1800. This loop can stop running. So every time this loop runs, we'll write the microseconds to our servo. Then we'll delay a short time just so we can see that movement. And once it gets to 1800, this loop will stop. The next loop is going to be very similar, only we're going to start at max pulse and go down to stop pulse. We're going to do this with our decrementer, I minus minus. So when we start at 1800, we'll go to 1799, 1798, all the way down to 1500. We're writing our data just the same, but whereas this goes from 1500 to 1800 up to get our full speed, we'll then slow down from 1800 down to 15. Now we'll ramp up in the other direction, so we'll go from our stop pulse down to our servo min pulse. When we're done there, we will ramp from our min pulse and we'll ramp our speed down to our stop pulse. So let's go ahead and run this and take a look. As you can see, we start getting counterclockwise motion. Our speed is going to go up and up and up. And eventually we start slowing down. We'll get to stopped. Then we're going to start ramping in the opposite direction. You'll see a little pause there because there's a dead band around 1500 before it actually starts. It's about a band of 5, so 1500 to 1505 is all stopped, and then at 1506 is where you start actually getting your motor speed. Now we happen to stop pretty close to where we were initially, but really it could be anywhere. It's just a matter of timing. So just to show how interchangeable a lot of this code is, let's take a look at Sketchbook, Robotgeek Sketches, RG101, 05 Servo, and we'll look at our analog in, servo out. And we'll actually look at F, analog in, servo out serial. So we're going to go ahead and we're going to try to adjust this right in the middle, our knob. We're going to upload our code. We'll open up our serial monitor. So I'm going to turn my knob here, and you can see that my speed goes up pretty quickly. I can bring it back the other way and have my speed this way. So let's have this starting to run. As we can see here, our raw analog value is 650. Our mapped servo value is 1743 microseconds. So let's take another look at our logic analyzer. And as we can see, that pulse, just like we'd expect, is 1719 microseconds. Just about what we expected from this mapped value. Now, one of the reasons that this is going to be top out, so here you can see, even at 2400, my speed is pretty much the same. This can be an important lesson, where both these servos look very similar, and they both plug in both plug in the same way, but they have different behaviors. So whereas here I'm adjusting the speed, if I plug in my individual servo, and again I'm running the exact same code, the exact same power, exact same board, and exact same interface, I'm going to be able to control the position of the servo. It all matters what's inside the servo, how it reacts to its external inputs. So now you can see why 4C continuous turn servos are so great for rovers. Easy to plug in, just like your other Robotgeek servos. You can plug them in alongside your other servos and use the same sort of control signals to get up and running right away. So that's it for this video. Make sure to check out more videos in Robotgeek 101.